Okay, so what we want to do here is basically undo the product rule of differentiation. Or something like that. And this is called integration by parts. So integration by parts. All right, so let's recall some things. First of all, if you take the derivative of f of x times g of x, you simply get f prime of x times g of x plus g prime of x times f of x, right? That's the product rule. So if we solve for this right here, we get that f of x times g prime of x, right, that's that right there, is equal to the derivative of f of x times g of x minus this, f prime of x, g of x. Really all I did was subtract, and then I moved them to the opposite sides of the equation. Now if I integrate this, each piece individually, which I can do because integration is a linear operator, I get the antiderivative of f of x times g prime of x dx is equal to the antiderivative of d dx of f of x g of x dx minus the antiderivative of f prime of x times g of x dx. I'm just anti-differentiating each thing. But this right here, the antiderivative of the derivative of fg, is simply fg. So the antiderivative of f times g prime is f of x times g of x minus the antiderivative of f prime times g. Now, what this is actually saying here is that we can write, if we have a product of some function and its derivative that is, that is a problem here, but it might not be a problem if we had a derivative, the derivative of f and, the antiderivative of g, then we can rewrite this antiderivative like this. And this we don't have to anti-differentiate because it's already anti-differentiated. And this might be easier than this. So this is called integration by parts. Now, we don't usually write it with f and g. We write it with u and v. So we're going to let u be f of x. Then du is simply f prime of x dx. We're going to let dv be g prime of x dx. So then v is g of x. So we're basically just writing u and v instead of f and g, and that gives us the following rule. So u is f, that's the antiderivative of u, dv is equal to u times v minus the antiderivative of v du. Okay, so this is how we usually write the formula for integration by parts. So we want to think about really, when is this going to be useful? First of all, we need a product. Okay, so u dv is a product. We need a product. We need u to be easy to differentiate, because we need to be able to write du. We need dv to be easy to anti-differentiate, because we need to be able to find v, and v is the antiderivative of dv, okay? And this works when the antiderivative of v du is easier than the antiderivative of u dv. Okay, make sure you're putting tails on your u's, otherwise you're going to get confused. So some common u's are x, ln x, e to the x, some common dv's are sine x, cosine x, sine x dx, cosine x dx, maybe even 1 dx, or say x to the n dx. And these are somewhat loose rules, right? It could be e to the x dx. You kind of have to just play with it and figure out what's going on. But we know we're looking for a product. We know u needs to be easy to differentiate, dv needs to be easy to antidifferentiate, and it works when the antiderivative of v du is easier than u dv. So really, we just need to try some things and see, but this comes up when substitution is not going to work and we have a product. So let's take, for example, the antiderivative of theta cosine theta d theta. Okay, so u substitution does not work here, because if we plugged in u, we would just get cosine of u times u, and that doesn't really help us at all. It's a product, so we can't antidifferentiate it super easily. Basically, we have a product here. We could let this be u and this be dv, or we could let cosine theta be u and theta d theta be dv. Well, I'm not sure. So let's just try one and see. All right, you kind of have to just see and see what happens, because both of those things are easy to antidifferentiate and differentiate. So let's let u be theta, and let's let dv be cosine theta d theta. Okay, remember, you need the antiderivative of u dv. So we need something that we can find the derivative of and something we can find the antiderivative of, and we need their product. And that's what we've got here. If u is theta and dv is cosine d theta, then this is u dv. Now we also need to find du, which is just simply d theta. And we need to find v, which is the antiderivative of this, which is sine of theta. So we have u, du, dv, and v, and now we're going to remember that the antiderivative of u dv is simply equal to u times v minus the antiderivative of v du. So this should be equal to u times v, that's theta sine theta, minus the antiderivative of v du. Oh yes, I'm good. v du, that is sine theta times d theta. Oh, look at that. Now that's really nice, because I know how to find the antiderivative of sine d theta. I don't have to worry about this because it's already been antidifferentiated. And I simply get theta sine theta minus negative cosine theta plus c, and that is simply theta sine theta plus cosine theta plus c. Now to check, I could take the derivative of this, and I would get theta times cosine theta plus sine theta times 1 minus sine theta plus 0. Boom, boom, equals theta cosine theta. So it definitely appears that this is going to work. I think my camera shifted. I apologize for that. Using an oven rack here. And it looks like that works. Now what if I had tried u is cosine theta, and dv is theta d theta? Okay, so what if I had tried the opposite, right? What if I had not been sure? Well then, du would be negative sine theta d theta, and v would be theta squared over 2. So this would become uv cosine theta times theta squared over 2 minus the antiderivative of v du, theta squared over 2 times negative sine theta d theta. Worse. That's worse. Oh shoot, I forgot to shift up there. This one is just worse. Theta squared over 2 times negative sine theta. I mean, this is bad. So, no, this one doesn't seem to work nearly as well. And we already did it the other way, so let's move on to another example. So ideally, you want du to be super simple. So that's why picking theta as your u makes your du d theta, which is super simple. Okay, let's try the definite integral from 2 to 3 of the natural log of x dx. Now, you may not see a product here, but don't forget about the old number 1, right? That's also a function. So if we let, say, dv be dx and u be ln x, we might think about what we could do with that. Now, why would we not want u to be, or rather, dv to be ln x? Because we have no idea how to find v in that case. In fact, that's what we're trying to do right here. So we don't want to do that. But if dv is dx, then v would be x. And if u is ln x, then du is 1 over x dx. So this should now become the integral, and I'm going to put over appropriate limits because I'm writing things in terms of u's and v's, and I don't really want to try and make that right. I guess it wouldn't become the integral over appropriate limits, but it would actually become uv, which is, you know what, I can keep this all in terms of x. I don't know why I'm changing it. But what it should become, rather, is uv, that's ln x times x. That needs to be evaluated between 2 and 3, by the way, minus the integral evaluated between 2 and 3 of v du. That would be x times 1 over x dx. Haha, that's awesome. So this is the natural log of x times x evaluated between 2 and 3 minus the integral from 2 to 3 of dx. And that's simply x ln x evaluated between 2 and 3 minus x evaluated between 2 and 3. So we actually see that the antiderivative of, man, I'm just keep shifting. This is very frustrating. The antiderivative of ln x is x ln x minus x, which we had seen before. And that's now between 2 and 3. So that should become 3 ln 3 minus 3 minus 2 ln 2 plus 2, because I'm distributing the negative, which is simply ln 9 minus ln of 4 minus 1, which is ln of 9/4 minus 1. So that is how I could write that one. But again, I'm using integration by parts to find this definite integral. Okay, where are we at? We're at 13 minutes. Let's pause this one, and we'll do another video with some examples.